Great, so today we're going to start looking at our second to last section for the class, which is 11.2. Okay, 11.2 is on a series. So basically what a series is when you take all the numbers in a sequence and add them up. For finite sequence, you can always do that because finite has an end. Even if it ends after the millionth term, you can still add up a million numbers. Maybe you need a computer to do it, but you can still do it. What gets a little more interesting is when you have an infinite amount of numbers and you want to add them up. Okay, so the question there is, well, can you add up an infinite amount of numbers? Sometimes. Depends on the numbers. So we'll look more at an infinite series tomorrow. So in the last section, we used this notation to represent a sequence, okay, a sub n. So I'm starting us off with a formula. It's a quadratic pattern to this sequence, which that would be kind of hard to figure out on your own. So a pattern that's quadratic, I'm probably not going to give you. I will show you a way you can figure it out on the graphing calculator, but not something I would expect you to do by hand. So here's the pattern for this sequence. It's 2n minus 1 squared. If you take a number and double it and subtract 1 from it, what kind of number would you always get? Yeah? An odd number. And that's kind of getting into number theory, which is a whole other thing. But the idea here is you're always squaring an odd number. Okay, so that's basically what this sequence is going to be, the odd numbers squared. Right, so what we'll do is let's write out some of the terms. So the first one you'd start with plugging in 1. 2 times 1 is 2. 2 minus 1 is 1 squared. That's the first one. Okay, I'll do one more and then you'll start to see the pattern that it's the odd squared. Plug in 2 for n. 2 times 2 is 4. 4 minus 1 is 3. 3 squared is the second one. Right? And then 5 squared all the way up to the nth term, which would be 2n minus 1 squared. That would be the last one. I don't know where it ends, but I'm just pretending that it ends somewhere. So now we're going to look at something a little different. Okay. When we put capital S sub n, capital S stands for sum. N stands for basically how many things you want to add up. So what this first one means, S sub 1, means to take your sequence and add up the first 1 terms in the sequence. Well, if you add up the first 1 terms, it's just the first term. S sub 2 would mean take your sequence and in what I just circled, add up the first 2 terms. So now it's 1 squared is the first one, plus 3 squared is the second one. All right, and now S sub 3 would mean to take your sequence and add up the first 3 terms. 1 squared plus 3 squared plus 5 squared. And S sub n would mean to add up the first n terms. That's what we would like to be able to get a formula for. Okay, because if we wanted to add up the first 500 terms in the sequence, there's got to be a faster way to do it than writing out all 500 terms and then adding them up. So in order to find a pattern for that, what we would do is look at this sequence. So this is a new sequence where each number in the sequence is a summation. So the first one is 1. The second one, in this particular problem, is 10. And the third one is 35. So I basically just did out the arithmetic. And we'd probably need a few more. But now what we would do is look at the sequence 1, 10, 35, and try to find a pattern for that. Okay. And if you can, then you can add up any amount of terms you want, okay, with a formula. So any questions on the notation S sub n? All right. So each individual term in that sequence I just wrote down, the 1, the 10, and the 35, those are what we call a finite series.
I apologize for the interruption. Any seniors?
Okay, so the reason it's called a finite series is because what you're doing is you're adding up a specific amount of terms. It doesn't go on forever. We're not there yet where we're talking about adding up infinitely many terms. So each specific S sub n is called a finite series. Even S sub 1. I know technically it's like you're not really adding anything up, it's just the first term. It's still called a finite series because it's just the sum of the first 1 terms. So kind of the next step, which I already showed you, is the sequence of partial sums is a new sequence. I think ours was 1, 10, 35. And it's a sequence where each number in the sequence represents a sum. S sub 5 would represent the sum of the first 5. S sub 20 would represent the sum of the first 20 in the sequence they give you. So that's called the sequence of partial sums, and that's kind of the goal. We want to find a formula for the sequence of partial sums. Okay, if we had to add up things by hand, maybe up to 10 or 20 terms, that's not too bad. But if you start to add up thousands or millions of terms, no, you gotta get a better way to do it than by hand. So here I'm just kind of breaking out what we did, but not using specific numbers. I'm just being very general. S sub 1 is just the first term. S sub 2, sum of the first 2. S sub 3, sum of the first 3. S sub n, sum of the first n terms. So this kind of problem can be multi-step, because now the first thing you have to do is find a formula for the sequence, and then once you have that, you can try to find a formula for the partial sums. Okay, some partial sums are pretty well known. They're very, very common. So we're going to have like some basic formulas that we can use. Some are really hard to figure out. Okay, but we're going to go through some common ones. Okay, and that last one, that's just called the nth partial sum. So next, I'm going to show you kind of a shorter way to write this stuff out. Because if you wanted to represent adding up 100 terms, to actually do it is another thing. But if you just want to write it down in a short way, I can show you how to write it in a short way. And that's called sigma notation. Has anyone used sigma notation before? It uses a big capital Greek letter. Looks kind of like a capital E a little bit. All right. Oh, let me show you. So let's say you wanted to add up all these numbers in that sequence, sequence A, up to the nth term in the sequence. Instead of writing A1 plus A2 plus A3 dot 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 plus AN, what you could write is this. So we start with this capital Greek letter. I said it looks kind of like an E, but that's a sigma. And then there's 3 things you have to fill in on the sigma. You have to fill in what term do you want to start adding up. In this particular sigma, we're starting with the first term. Where are you going to end? Okay, you're going to end at the nth term. So now you've told me where to start and where to stop, but what's the formula for what you're adding up? Right there. So on the right-hand side, what I just circled, that's the kind of thing you figured out yesterday. That would be the formula for your sequence. And what you do is you start at 1, and you plug in every single number from 1 up to n into that formula, okay, one at a time. So it's not a quick way to do the calculation at all. It's just a quick way to write it down. That's all it is. So let's look at We'll look at an example. So the way you'd pronounce this is the sum from k equals 1 to m of your sequence. And pronounce your sequence, a sub k. Now, k is called the index of the summation. It's basically, in like computer language, it's like a counter. It's a variable that just keeps track of, okay, what term are we adding up? The first one. Now we're at the second one. Now we're at the third one. It just keeps track of what numbers you're plugging into your sequence. All right, so let's actually do this one out, because we're only adding up 5 numbers. So you're starting by plugging in 1 for k. You're going to stop when you get to 5. And what formula are you going to plug them into? 2k plus 3. So what we're going to do right now is it's called expanding. We're going to expand that sum out. So start with k equals 1. If you plug in 1 for k, what would be the first number that you have? Yeah, you have 5. Plus, how do you know to put a plus? You've got that big capital sigma. That means put a plus. Okay. Now we go to the next number, 2. So you go up by ones. If you plug in 2 for k, what do you get here? Yep, 7. And then if you plug in 3 for k, 2 times 3 is 6, plus 3 is 9. If you plug in 4 for k, you get 11. And you keep going until you hit that limit. Now you plug in 5 for k, 13. Now you wouldn't plug in 6 because we stopped at 5. So that notation on the left means to do that thing that I just did on the right. Okay. Any question on that? Now, I'm going to show you another way to write that exact same thing. It's going to look different, but the answer is going to be exactly the same. What this is called is reindexing. I'm going to, instead of plugging in 0 as my first number, I want to plug in, instead of plugging in 1, I want to plug in 0. I can start wherever I want. I'm going to go 0 to 4. But I can't use the same formula, because if I use the same formula, I'm going to get a different result. So I have to adjust my formula a little bit. And I have to adjust it by going like this. Not going to explain too much about this right now. So this should work. 2k plus 5. This should be exactly the same thing I just got. If you plug in 0 for k, 2 times 0 is 0. 0 plus 5 is 5. So now plugging in 0 gave me my first term. Plugging in 1 should give me my second term. 2 times 1 is 2. 2 plus 5 is 7. Okay, any questions on that? Or not how I got the 2k plus 5, but just the fact that it's going to give me the same result. So that name for what I just did, that's called reindexing. And the reason why you might have to do that sometime is because if you had multiple summations and you want to combine them together, they have to basically be like terms. You can't combine a sum that starts at 1 with a sum that starts at 0. Okay? They have to start at the same spot and end at the same spot. All right? So I just made an adjustment. And the way I kind of did it is basically if you take that number and bring it down 1, so it started at 1, you brought it down to 0, you have to balance it by bringing the other one up 1. So I brought the k down 1 to 0, and I'm going to bring the k here up 1. So whatever you do, you just have to keep it balanced. If I wanted to start at like, 2, okay, I'm bringing the k up 1. In the formula, I bring it down 1, make it a k minus 1, and that kind of keeps things balanced. All right, you're not really going to have to do a ton of stuff with that, but I'm just showing you. In case you see sums that start with different numbers, that's okay. So that notation is called sigma notation. When you actually write it all out, you're expanding it. That's expanded notation. So looking back at what we did, sigma notation on the left, expanded notation on the right. Now, even though this is kind of a nice, short, compact way of writing things, it doesn't do anything to speed up calculations. If you actually want to know the answer to a problem that has sigma in it, you still got to do the whole thing out. So eventually what we want to do is come up with some formulas where if we see common summations, okay, some common ones that come up, we can substitute for that a formula and get rid of the sigma. Okay, that's kind of the goal. We want to be able to get rid of sigmas whenever we can. All right, let's do this one just because it's a little different. Is this a finite sum or an infinite sum? We're going from 1 to n. Yep. Infinite. No, not infinite. It is finite. Yeah.
No, it's finite because it gives you a stopping point.
Yeah. It gives us a stopping point. The stopping point is n. We don't know n, but it's the stopping point, even though we don't know what number it is. So the way you would show this out is just do the first 3 or 4, and then put a dot, 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 and then do the last one. So if we do the first one, 2 times 1 plus 3. Gracie, what does that give me if I plug in 1 for k?
5.
Yeah, and we can just leave it as 5 squared. That's fine. So we get 5 squared. Plus, now let's do the next one. Jay, and what would the next one be?
7 squared.
7 squared. Plus, and then the next one would be 9 squared. Okay, at this point, I think we've established enough of a pattern. Somebody can see what's going on. Oh, we're squaring the odd numbers starting at 5. Plus, put in a dot, 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 because there's an undetermined amount of terms between the third term and the last one. Now, what do I plug in for k at the last step? N. So 2n plus 3 squared. That's how you would expand that. You'll know when it's infinite because in place of the n, you'll have the infinity symbol. And if that was in this problem, I would put a dot, dot, dot at the end. Okay, but we're not going to look at that today. Questions on that? All right. So now we're going to look at some properties of summations. So where we're kind of going with this is we want to be able to combine these 2 summations into one. And this one is set up ready to go because they both start at the same spot. They both stop at the same spot. So we're good. That's combinable. And you basically do it exactly the way you would think. You just put one summation, keep the bottom and the top the same, and then just combine your like terms in each sequence. That's basically what happens. But we'll go through the formulas. So, you're going to use this rule on the first problem. Basically, in the first problem, I'm giving you this. 2 separate sums, and I want you to combine them into a single sum. When you combine them into a single sum, keep the starting point and the stopping point the same, and just take whatever you have here and whatever you have here and add them up. Okay, add the 2 sequences, I'm calling them A and B, by combining like terms. So in this one, you could think of that as sequence A, that's sequence B, add them up. Okay, and for the first one, I'll kind of show you why it works. I'm not going to go through this with all of them, but I'll just make up 2 very simple sequences, very short. Let's let A sub k be the sequence 1, 3, 5. Very short, simple sequence. Let's let B sub k be the sequence 2, 4, 6. So let's do it one way. Let's do what's on the left first, and then let's do what's on the right. So on the left, order of operations, they put parentheses around that. So they're saying add up sequence A and sequence B first. And the way you add two sequences together is you just add the corresponding terms. So those two get added, those two get added, and those two get added. And that's going to create a new sequence. So A sub k plus B sub k equals 1 plus 2. Gives me the new first term 3. 3 plus 4 gives me 7. 5 plus 6 gives me 11. Okay. Any questions on that? Now, we take into account the whole thing. It says now to add up, in this case it's only to 3, add up all the terms in the thing you just created. Okay. So let's add them all up. So 3 plus 7 plus 11 gives me how much? 21. So when we add them, I'm just going to kind of put it over here. When we add them all up, we get 21, because I'm out of space. Now, doing it the way on the right, it says, okay, there's no parentheses around that. So it says, take all the numbers in sequence A and add them up. 1 plus 3 plus 5 gives me how much? 9. Plus, take all the numbers in sequence B, add them up. 2 plus 4 plus 6. 12. And now, take the two separate results, add them together. 9 plus 12, 21. So, that doesn't prove it, but it just shows you with a specific example that you can take two summations and combine them into one. Okay? You can do the same thing with subtraction. So rule 2, you basically could just put minuses if you don't want to write the whole thing again, but it's the same rule with subtraction. Honestly, I would just put plus or minus, and that takes care of writing the whole rule for number 2. And then rule 3 is a little different. It has to do with when your sequence is multiplied by a constant. Okay, so let's do this one out, and let's copy down what sequence A was. 1, 3, 5. All right, now I'm going to pick a constant. I'm going to let my constant be, it doesn't matter, I don't know, 2. So on the left, what it's saying to do is first do C times your constant. You're always going to do your multiplication. Think of it as a dot right there. Do multiplication before addition. All right. So the way you multiply a sequence by a constant, it's like a distributive. Multiply every number in the sequence by your constant. So C times A sub k would give me a new sequence. And what would be the terms in C, A sub k? We've got A sub k and we've got C. Let's put it together. Yep. 2, 6, 10. Now it says add. Add everything in that new sequence. So now we get 2 plus 6 plus 10 gives me 18. And that's the sum of all the terms. Specifically, we just went from 1 to 3, but that's fine. All right, so we get 18. Now, the way on the right, let's see, it says you handle the summation first. So first, add up all the numbers in sequence A, and then multiply by C. So let's do it that way. 1 plus 3 plus 5 gives me 9. My value for C is 2. 2 times 9, 18, 18. So when you have a sequence multiplied by a constant, the trick, you can put the constant in front. Okay. So any questions on those 3 basic rules? All right, so now let's use them on this problem. So I want to combine that into a single sum. when I combine it, do I change my starting or stopping point? Those get changed. Leo?
No, they're the same.
No, they're the same. You can only combine them if they're the same. If you notice, my sigmas start to get a little sloppy as I go on. The top, if I want to draw one really nice one time for you, it should look like that. It shouldn't be slanted, but I don't know why. When I draw it fast, it just comes out slanted. All right. So from k equals 1 to n. And now just combine your like terms. When I combine the two things I just underlined, what's going to be the squared term? Yep. Yep. So 6k squared. And the linear term? Yep. Yep. Negative 2k. And the constant? Negative 4 plus 7 gives me, yeah, positive 3. So there's a quadratic sequence being summed from 1 to n, but we've taken and combined it all into one summation versus 2. Okay, questions on that?
Would that be a final answer?
Yes. Yep. Now, sometimes for this kind of problem where the directions just say combine into a single sum, yes, that's the final answer. For the next thing we're going to do, we're going to go one more step with that. Okay, but you'll have some that are just like this, and then some that take it the next step. So this is what I've said before. Sigma notation is a nice compact way of writing things down. But if you actually still want to know the answer to this, you still got to calculate the whole thing out. So now our goal is going to be, how can we get rid of the sigma here? I don't want the sigma. Okay, so we'll look at how to do that next. So let's look at this one. This says to add up, well, actually, you tell me. What is this basically saying to do? If you wanted to explain that in terms that somebody in like 4th grade could understand. Because they'd look at that and they'd be like, what? Yeah?
Add up every number 1 through 10.
Add up every number 1 through 10. That's it. Okay, so add up all the numbers 1 through 10. So here's our list. And let's start to create a sequence of the partial sums. And then I'm going to show you how you can use the calculator to find the pattern for it, because it's not an easy pattern to find by hand. If you add up the first 1 terms in that sequence, what do you get? Yep, 1. What if you add up the first 2 terms in that sequence? What do you get? 3? Sean, in the first 3 terms? 6. First 4 terms is going to be 10, and then 15, 21. I lost track where I was. So first, I added 5, I added 6. So the next one would be add 7. So 21 plus 7 is 28. Okay. So that's the sequence of partial sums. I want to find a pattern for that. Okay. So basically, this is the position number. I want some arithmetic that I can do with 6 to get 21. And I want to be able to do that same arithmetic with 5 and get 15. Now, you're probably not going to be able to guess this one. It's not arithmetic, it's not geometric. But I can give you a hint of how you can figure out what it is. So, you can keep the commas, but it'll look less confusing if I do this. What's 3 minus 1? 2. 6 minus 3, and 10 minus 6, 4, 5, 6, 7. Now, let's do that same thing one more time. What's 3 minus 2? 1. 4 minus 3? So now we're getting a row of all 1s. This doesn't tell you what the answer is to the formula, but it does tell me what kind of formula it is. It's quadratic. How do I know? Because I had to do this little tree process 1, 2 times, and then I got a row of constants. That doesn't always work. Like if you try this with the Fibonacci sequence, you'll never get a row of constants. You'll just keep subtracting numbers that never, ever come out the same. But in a polynomial formula, if it's polynomial, however many times you have to do this subtraction process is what the order of your formula is. We did it twice, so it's an order 2. It's a quadratic. Now, knowing it's a quadratic, I can type it into the calculator, and the calculator can tell me the formula. So this might be kind of new, but the way you do it is under Stat. You go to Edit, and think of these as ordered pairs. Plug in 2, you get 3. Plug in 3, you get 6. Plug in 4, you get 10. Plug in 5, you get 15. So they're like XY values. For some formula, we don't know. So we can type them in. If you plug in 1, let's just write some out. That's plenty. We don't need them all. If you plug in 1, you get 1. If you plug in 2, you get 3. 3, you get 6. If you plug in 4, you get 10. 5, you get 15. So that's the first. Tell the calculator what you want to type in. The next step is to go back to statistics, and we want to calculate a regression line. Now, we already know what kind of regression line it should be. It's quadratic. And the way we figured that out is that little difference thing. So go down to quadratic. So you're going to tell the calculator, you've got to be a little smart and say, hey, I know it's quadratic. You look for a quadratic pattern in this and tell me what you get. So tell the calculator to look for a quadratic pattern. If you put your x's in L1 and your y's in L2, like I did, there's nothing to change there. So go to calculate, and it gives us a pattern. So it's of the form ax squared plus bx plus c, where a is a half, b is a half, and c is 0. Right? Let's try that. So ax squared plus bx plus c, a is a half, b is a half, and c is 0. Okay, what I'm going to do to kind of neaten that up a little bit is you can factor out a 1/2 x from it. If you factor that out, you're left with x plus 1. And the last thing is, instead of multiplying by a half, that's the same as dividing by what? 2. So I'm going to write it like this. I think most people will find that a little cleaner. That's the formula for the sequence of partial sums to add up the first n integers. Let's try it. If we add up the first 5 integers, the answer should be 15. 5 plus 1 gives me how much? 6 times 5? 30. And 30 divided by 2? 15. If we add up the first 6, 6 plus 1 is 7. 7 times 6 is 42. 42 divided by 2, 21. So now we just found a pattern to add up the first n integers. So now if you wanted me to add up the first 100 integers, I don't have to do it that way. I can just say it's 101 times 100 divided by 2. Whatever that comes out to, that's what the first 100 integers would add up to. And that's a common pattern, okay, adding up the first n integers. So I'm gonna write that down along with 2 other ones on the next page. So I'll write this a little nicer. I just wanted to kind of show you how to get that, which the calculator can do. I like it written like this rather than like you would like a quadratic equation. I just think it looks a little nicer. X times x plus 1 over 2. It's the same thing. All right, so even though we've said this, it's a compact notation, you still have to do it out by hand unless you can figure out a formula that allows you to get rid of the summation. Okay, so let's look at a few common, this is actually what we just went through, okay, filling out the table. I just put it right here. Okay, so I'm not going to go through all that again, finding the formula. Okay, so now we'll look at some common formulas, including the one we just did. But there's actually one that's even a little easier than that. So these are formulas that take a sigma and get rid of it. Okay, remember, sigma, nice way to write things down, doesn't actually speed up any calculations at all. So we want to get rid of sigmas when we can. So we're going to look at 3 different formulas. We already did this one. This is adding up the first n integers. The last one is adding up the first n perfect squares. 1 plus 4 plus 9 plus 16 plus 25 plus 36, okay, and so on. But let's look at this first one. It's the sum from 1 to n of a constant. Sum from 1 to n of a constant. So let me give you an example. The sum from 1 to 5 of the constant 3. So what you're supposed to do with this is you take 1, you plug it into your formula on the right-hand side, get the answer, write it down, and then plug in 2, and then 3, 4, and 5. If you plug 1 into that formula, what do you get? Yeah? 3. There is no spot to plug it in, it's a constant. So you get 3 plus. What if you plug 2 into the formula? Yep, 3. If you plug 3 into the formula, you get 3. If you plug 4 in, you get 3. If you plug 5 in, and that's the stopping point, you get 3. How many 3's do we have? We have 5 of them. 3 times 5. That's the answer. So when you're adding up a constant over and over, it's just your constant times your stopping point. Your constant times your stopping point. C times n. So that's an easy one. The second one we just did. Adding up, I'm using the letter n now. You can use x, but I'm using n. To add up the first n integers, it's n times n plus 1 over 2. Now, for certain things, it is going to be better to have that foiled out and written the way it was before, like 1/2 n squared plus 1/2 n. That is going to be better for some things. So if you want to write it that way too, you can. Make sure you write it correctly. And then the third one, I'm not going to go through it, but it ends up being a cubic pattern. So to add up the first n integers, it's a quadratic pattern. To add up perfect squares, it's a cubic pattern. And it's n times n plus 1 times 2n plus 1, all divided by 6. There is a formula for perfect cubes. You don't have to worry about this one, because at this point, it's going to start to take a long time to go through the algebra. In fact, I think this formula might even be worse than the one below it. Okay, let's get rid of that. And let's do that out a little bit, because that'll save us some time when we have to do the problem. So let's just start by distributing the n. So you get n squared plus n times 2n plus 1 all over 6. And now, what do I have to do to multiply out those 2 sets of parentheses in the top? Trevor?
Distribute.
Yeah, we just distribute it. So Gracie, what's n squared times 2n?
2n cubed.
Yep, 2n cubed. And Sam, n squared times n? I'm sorry, n squared times 1?
Oh, me?
Yeah.
Oh, sorry. N squared times 1.
Yep.
N squared.
N squared. We've got n times 2n. That's a 2n squared. And then we have n times 1, which Jn gives me n. Let's just make sure we did it right. 2n cubed plus n squared plus 2n squared plus n, all divided by 6. So what I'm going to do is go like this, because some of these reduce. I could combine like terms. So I'm going to get 1/3 n cubed. I'm going to get 1n squared plus 2n squared. That's 3n squared over 6. Plus, you can write n over 6 or 1/6 n, same thing. I'm just trying to write it as a polynomial all distributed out, because that's going to save us a ton of time if we do it this way. So 1/3 n cubed plus 1/2 n squared plus 1/6 n. So that's the formula if you want to add up the first n perfect squares. So if you wanted to add up all the numbers squared from 1 to 10, so 1, 4, 9, 16, all the way up to 100, all you would do is plug in 10 for n, and this formula would tell you the answer, and it would automatically do all of that for you. So any questions about these formulas? All right, so now let's take a problem and see if we can get rid of the sum. So what we want to do here is kind of the reverse of what we did. Break this apart. Okay? And basically, to break it apart, you're just going to, it's not really called distributive, but it's kind of like distributing the sum back out to each term. So we would get sum from k equals 1 to n. And we're going to have another one. So it's just the reverse of what we did before. The first one is going to have negative 2k. Copy down your plus. And the second one has a 3. Now, this part we should recognize. That's the sum from k equals 1 to n of a constant. The sum from k equals 1 to n of a constant. So in a minute, we can substitute and get rid of that sigma. Okay, it's just the constant times n. But this isn't one we recognize. We never had one with a negative 2k. We had one with just a k. But we had another rule that said something you can do with this negative 2. What are you allowed to do with that negative 2? Yeah?
You can pull it out of the
We can take it and put it in front. So now we have negative 2 times the sum from k equals 1 to n of k. That's something we can substitute for. There's a formula to do that. That's the one I showed you on the graphing calculator. Plus the sum from k equals 1 to n of 3. That's another formula we can substitute for. So now we'll just substitute in. Let's look up the formula from 1 to n of k. 1 to n of k. It's easier if you use it FOILed out. So it's 1/2 n squared plus 1/2 n. So 1/2 n squared plus 1/2 n. That's what's in the box. Don't forget about the negative 2 in front. Plus from 1 to n of the constant 3. From 1 to n of the constant and minus 3. So what would that second box turn into? Yeah? 3n. And now that you've done that, from here just do it out, combine like terms, and make it look nice. So distribute, and you get negative n squared minus n plus 3n. You can see how much time it saves if you have the FOILed version written down. You don't have to do it right now. And then combine that. So negative n squared plus 2n. So now, in this particular formula, if I said to you, add every number from 1 to 1,000 using this formula, the old way, you'd plug in every number from 1 to 1,000 for k, write down every calculation, and then add them all up. The new way, just plug in 1,000 for n, and that's your answer. So it's negative 1,000 squared plus 2,000, and that would be it. Any questions on that one? All right, let's try this one, and then I think that's the last. All right, let's just get this one at least to the point where there's no sigmas in it. When I split that up, how many sigma symbols am I going to have? Yeah, I'm going to have 3. They're all k equals 1 to n. And what's the first one going to be? And if I can move any numbers in front, I would like to do that. Yep.
2 and k squared.
So 2k squared. Copy down your plus. You have a formula you could go look up for that. Okay. What's the next one going to be? Okay.
You have 5 on the left, and then k.
Yep, so 5 times the sum from k equals 1 to n of k. You have a formula we just used. You could go look up for that. Minus, just copy the minus. And you have a formula you could look up for that. So now you just have to substitute in for those 3 black boxes and then distribute combined like terms. But any questions on how you'd finish that up from here? Okay. So, last thing. We're going to focus specifically on a geometric series. And what we want to come up with is a quick way to add up a bunch of numbers if the sequence is geometric. So remember, geometric sequence would be something like 2, 4, 8, 16, 32, 64. It's multiplying by the same number each time. And that's what this basically says. You've got your first term. The second term is the first one times the number. The third one is the one before it times the same number again. And the next one would be a sub 1r cubed, a sub 1r to the fourth, all the way up to a sub 1r to the n minus 1, because remember, to get to the third term, you've multiplied by r, 1, 2. So it's always 1 less than the term you're at. Okay, so let's write down what S sub n would be. S sub n is when you take all the numbers in that sequence and add them up. So basically, just write that down with plus signs instead of commas. So it's a sub 1 plus a sub 1 r plus a sub 1 r squared. If you want to add another one, you can. A sub 1 r cubed. All the way up to the last one. A sub 1 r to the n minus 1. Now, the next thing I'm going to do, at first you're going to be like, why is he doing that? For now, don't worry about why I'm doing it. Let's just do it, and I'm going to show you something that happens in a second. I want to find r times s sub n. So all that means is every term in s sub n is getting multiplied by r. So what would that make the first term if it got multiplied by r? Yep. A sub 1 r. What would that make the second term? Yeah.
A sub 1 r squared.
Yeah, make it a sub 1 r squared plus a sub 1 r cubed plus a sub 1 r to the fourth plus. And what would the last term become? Yeah.
A sub 1 r to n.
A sub 1 r to the n. Now, that term is right there. I didn't write it, but that would be the term before this one. Because you'd have r to the fourth, r to the fifth, and then whatever, you'd have the one before to the nth power, and then you'd have the nth power. So that term would be in that sequence. I just didn't write, I can't write every term in the dot, 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 because it goes on forever. Or it goes on for a long time. All right, now, I want to subtract those two and see what happens. I want to take this and I want to subtract that. The two things that I just circled, do they have any terms in common? Megan? Yeah, a lot. In fact, almost every term in common. Okay. So let's look at a sub 1. Does that appear in the sequence below? No, that's one they don't have in common. But let's look at the second one. A sub 1r, does that appear in the one below? Then when we subtract, they would cancel. How about a sub 1r squared? When we subtract, they would cancel. A sub 1r cubed? Yep. A sub 1r to the fourth? Yep. That would be in the dot, dot, dot somewhere. How about a sub 1r to the n minus 1? Is that in the last one? Yeah, that would be in the dot, dot, dot down here. So, if you subtract them, all you're left with is a sub 1 is the only term left in the top. Everything else would cancel out. And in the bottom, you're also left with one thing, a sub 1 r to the n. That's not in the top one. That would be over here. It would be after the last one. We can't go after the last one. So minus a sub 1 r to the n. Okay, any questions on that? All right, so now I want to look at that. Do I look at it on this page? No. Let's look at it right here. Let's, we're trying to find a formula for this, S sub n. Okay, and in a second, I'm going to show you what the formula is. Let's see, what can we do? Let's factor out S sub n. Since it's in both spots on the left-hand side, I can factor it out. If you factor it out of the first term, what are you left with? 1. And what if you factor it out of the second term? You're left with an r. Right, and yeah, for now, let's just leave the other side the same. I know I could factor out a sub 1, and I am going to do that eventually because they have the same thing in common, just like the other side, but just leave it like this. Now, I want to get that by itself. That's S sub n times 1 minus r. So how could I move the 1 minus r to the other side? Divide. Now, I just got S sub n by itself. What does that mean? I have a formula to add up the first n numbers in a geometric sequence. It's a sub 1 minus a sub 1 r to the n all over 1 minus r. Or a little bit neater way, if you factor out the a sub 1, it's a sub 1. Factor it out of the top, you're left with a 1 minus r to the n all over 1 minus r. That is the formula for adding up the first n terms in a geometric sequence. The word closed here means there's no sigma. Okay? When you have a sigma as part of a formula, that's not a closed formula, okay? Because it's not easy to work with. That's a closed formula. There's no sigmas. All you have to do is know what r is. That's what you multiply by each time. And n is how many numbers you want to add up. You want to add up the first 10, 20, plug in whatever you want to add up to. So the way I figured that formula out, though, that was a little tricky. There might be other ways to figure it out, but that little trick of doing these two things and then subtracting them is probably the most common way to figure it out. But probably wouldn't think of that on your own. Okay, so let's finish up by using that formula to add up the first n terms in a geometric sequence. Okay, so they want me to take this and add up the first 12 terms. Well, first we got to figure out what's happening. What am I multiplying by each time? Yeah, a third. So we're multiplying by a third. Okay, so we've got r. we need the first term. You've got that. A sub 1 is 2. And n is how many terms we're adding up. How many do they want me to add? Yep, 12. So now just fill in those 3 numbers into the formula. So if you add up the first 12 terms, it's a sub 1 times 1 minus r to the 12th, all over 1 minus r, but let me simplify that. What's 1 minus a third? Leo?
Negative 1/3. Well, or no, 3. I'm done. Hang on.
Yep.
2/3.
2/3. Okay, so let's see what we get if we type that in. Easiest way to type that in is probably in stages. So let's do 1 minus 1/3, close parentheses. That way the exponent of 12 will apply to the whole thing. Divided by 2/3. Let's put that in parentheses. Times 2. So if you add up the first 12 terms in this sequence, you get that. So S sub 12, let's try again. S sub 12 equals 2.999994355. What's happening to the terms in the sequence? 2, 2/3, 2/9. I know they're multiplying by 1/3 each time, but what does that mean? They're getting closer to what? Yep. They're getting closer to 0. So there's your second term. There's your third term. That's 2/9. Fourth term, 5th, 6th, 7th, 8th. Now I'm in scientific notation because there's so many zeros. So what's happening is if you continue this sequence forever, eventually it's insignificantly small what you're adding. So this is a sequence where if you did add up every number in it forever, it would approach a certain number. I think just adding up the first 12, you can already see what it is approaching. So tomorrow we'll kind of extend that idea and talk about, well, what happens if this sequence went on forever? What did we get for an answer? But for today, we'll stop with that. All right, so the homework tonight is it's on 601. And let's see, you can skip 11 and 12 here. It's probably easier to just write it that way. So 1 through 17 all, but skip 11 and 12.